Hello everyone, welcome to another video. Today I'm going to be looking at all the calculus you need to know for A-levels, maths, and further maths. So this is going to be all of the calculus. I'm going to tell you guys which parts are needed only for maths and which parts are needed for further maths. And I will be giving you guys timestamps, so if you want to skip to the sections you want to look at, then please go ahead. But yeah, I just wanted to make one video on everything you needed to know so it's easier for you guys. So yeah, let's first begin with general integration. So this is the basic integration that I would think you need to memorize. Of course, there's techniques that you can use for integration, but these are some of the simple integrations that you need to memorize. So integrating e to the x gives you e to the x, very simple. 1 over x gives you ln x, sine gives you minus cos, cos gives you sine. So these, I would say, are needed for maths. And then if you do further maths, then you would need to know the hyperbolics. So these are the hyperbolic integrations. So these are not given in your data booklet, so I would recommend you to memorize these. So sine, or that's how I say it at least, would equals cosh, and cosh would give you sine. Tang will give you ln cosh, and sec squared would give you tang. In the description down below, I'm going to put all of the notes that I look over for this, for all the things that you memorize, so you don't have to jot down everything. You can just print it off in the description's link. So yeah, it'll be easier for you guys that way. So same thing here, but with differentiation. These are some general differentiation problems that you should know. Sine will give you cos, cos gives you sine, tan gives you sec squared. A to the power of x would give you a to the power of x times ln a. So this is kind of like the chain rule, which I will go into deeper further on in the video. So this is just the function multiplied by the derivative of the function. This is very handy to memorize because it has come up in a lot of past paper questions before. And then here as well, differentiating a logarithm will give you 1 over x ln a. Then from here onwards, it's further maths of hyperbolic integration. So sine will give you cosh, cosh will give you sine, tang will give you sec squared x, or if you want to use the identity, it gives you 1 minus tang squared x. And then here you can use this for maths as well. E to the power of x differentiated would give you e to the power of x, so it's unchanged. So these are some basic integration differentiation that you should memorize. It will make your life 10,000 times more easier during the exams if you just memorize them. Let's first look at some integration techniques. So this one is useful for maths and further maths. So for further maths, I'll write f, and for maths, I'll write a small m. I guess that also spells out further maths, but I hope you know what I mean. So I have an integral where the numerator is the derivative of the denominator. Then integrating that will give you ln of just the denominator, which is fx. So you can see it's just the denominator you just put into ln. Don't forget the absolute value sign. So here is an example of what I mean. If you have tang, so again, this is a hyperbolic function. If you don't do maths, then you probably aren't familiar with this. Integrating tang will give you 1 minus tang squared x, as you've seen here. So integrating that will give you ln tang x. Looking at more of a normal maths example. So x squared plus 1 is the denominator and 2x is the numerator. If you were to differentiate x squared plus 1, you would get 2x, which is the numerator. So you can say ln x squared plus 1. Now the second integration technique that you need to know is integration by parts. So this is for maths as well. And the general rule of this is uv minus integral of v times, so these are multiplied together, derivative of u dx. So this is the whole function. So let's look at an example to see what I am talking about. If you have x sine 2x, then you need to make one of these functions. So you can see this as two functions multiplied together. So this can be f of x, and this can be g of x. So these are two functions multiplied together, and you need to assign one of these functions to u and one of these functions to x. Now, to know which one to assign can be kind of tricky. You would just have to go forth with the integration, picking either one, and then see if you get an even more complicated integral here, or if you get a more simplistic integral that you can find quite easily. If it's more complicated, then that's a sign that you probably picked the wrong function. So you might want to try and pick the opposite one to see if you get an integral here that you can potentially solve. Sometimes though, you might have to use integration by parts twice, so you might have to have another integration by parts in this integral. But again, you have to go forth with the integration to actually see if it's going to work out or not. But anyways, in this case, using u as x works, and derivative of v. So first we're going to make g of x equal the derivative of v. And to make the derivative turn into the actual function v, we would have to integrate the derivative. So integrating sine 2x would give you minus cos 2x divided by 2. We should know this from simple trig integration. If you don't know how to do simple trig integration, it basically is that since we know the integral of sine x is minus cos x, dividing whatever is the derivative of your function of x. So here we have 2x, the derivative of this is 2, so dividing by the derivative would be 1 over 2. So this is basically minus 1, this is basically 1 over 2 times minus cos 2x. So I hope you can see where that's coming from. Alright, so now we just apply the rule that we have here, and we just make u, which is x, multiplied by v, plus integral of v, which is this. All I've done here is taking out the 1 over 2 because it's a constant. So in a integration, you can basically take out any constants that you have because they will remain unchanged. So I have a minus half here in the front, so I just took that out to make it more simplistic, so it's easier to integrate. And then once we integrate that, once we integrate cos 2x, we get sine 2x over 2, and then multiplied by this half. We cannot forget that. And of course, add r plus c. And now we have this, which is our final answer. So I hope you can see how by parts is done. Now let's move on to integration by substitution. So this is another method that you can use to integrate more complex functions. And this is basically just letting a part of the integral, a part of the function, equal to u. So how we use this is, if we have this very complex integral that we don't know how to integrate, we can use a part of this integral and make it equal to u, and then use that to substitute back into the integral, and then integrate it in terms of with respect to u. So if we let u equal x squared plus 4x, and then what we have to do is we find the derivative of u. So the derivative of this would be 2x plus 4. And then what we do is we bring this dx to this side. So we get du equals 2, I've just factorized the 2 out, brackets x plus 2 dx. Now what we can do is write as du over 2 equals x plus 2 dx. So now we have x plus 2 dx over here on top. So we can substitute this to be du over 2. And since we made this equal to u, we just substitute that back in as well. So now, again, I've taken out the constant a half, and then we are left to integrate u minus to the power of minus a half, because this surd is to the power of half, and then if you bring it on top, they'll become minus a half. So integrating that will give us this, and then we can substitute back our u. So all I've done is substituted u to be x squared plus 4x to the power of a half, and I multiplied a half times 1 over a half, which is 4. So we have 4 root x squared plus 4x plus c. So I hope you can see how integration by substitution is done.
So another rule I want to talk about is the reverse chain rule. And this is basically used when you have a function in a function. So if one function, in this case, is ax plus b, and the other function is y over n, so the y being ax plus b. Now the way you want to solve this is first just do normal integration of the y over n function. So we just make n plus 1 and we divide by n plus 1. But what we do now is we divide that integral with the derivative of the function inside the function, which in this case is the derivative of ax plus b. So here, as you can see, they've divided by 1 over a, and then the normal function integration applies. So if we look at the example here, we have x minus 5 as one function and the function of y to the power of 8. So we solve this by first integrating x minus 5 over 8 by just ignoring x minus 5 and just integrating y to the power of 8 normally. So that will be 1 over 9 y to the power of 9. And then we substitute the y for x minus 5, and then we divide by the derivative of x minus 5, which in this case is 1. So it's just divided by 1, and we get 1 over 9 brackets x minus 5 all to the power of 9.
Another type of integration problem that I want to look at is one involving rational functions. So when you have a rational function like this, where you can factorize the denominator, then it's most likely that you have to use partial fractions to solve it. So if we look at this example here, I have basically separated this into 3 different fractions to make it more easier to integrate all together. And now, using the regular partial fraction technique, I have basically just expanded the brackets and then compared coefficients with the actual numerator, and then just solve it simultaneously using that comparing coefficients method to find 1, minus 2, and 2 for ABC. And now we have separated them into 3 different fractions. It's much easier to solve them because we can integrate them one by one. So let's look at integrating 1 over x minus 1. So we know that integrating 1 over x gives us ln x, but then integrating 1 over x minus 1 would give us ln x minus 1. This is because the derivative of x minus 1 is still 1. So all we have to do is use the reverse chain rule. So we have to essentially divide ln x minus 1 by the derivative of x minus 1, which is just 1. So what remaining is ln x minus 1. Now the same thing applies for the minus 2 over x plus 2. So that gives us minus 2 ln x plus 2. And then here in the third one, we have 2 over x plus 2 all squared. Here you need to be careful to not be quick to assume that it's an ln for an integral, because when you make the x plus 2 go up, it will lead to the power of minus 2, and we can integrate a bracket to the power of minus 2. So this is similar to the reverse chain rule example that I showed before, but in this case the derivative of x plus 2 is just 1, so we just divide by 1. And then adding a plus 1 to the power gives us minus 1, and then dividing that minus 1 with the whole term gives us minus 2. This is just the normal integration of the n plus 1 rule that we're using here, and that should give you your final answer. Now let's look at some basic differentiation techniques. So the first one is the chain rule. So now for the chain rule, this is the general rule that you have to apply. And what does this mean? Basically, if you have a function of x and in that function you have another function, so differentiating that would mean the derivative of the function of x with the function of g of x in the function of x times the derivative of g of x. That is a mouthful, but so I'll show you how it's actually done. So if you have this, where f of x would be, so 5 squared plus 3x minus 1 would be considered g of x, and f of x would be this to the power of a half, which is this third. So what we can do to see f of x more clearer is make this and write it as, for example, u. So you have y equals root u. If you had to differentiate this, then this would just be half u to the minus half. And what we can do is substitute this u back in, and this is what we get. So I hope that is clear. And then we just multiply it by the derivative of u, which is the derivative of this bracket inside the third. And that will give you a 10x plus 3. And just rewriting this and just rearranging, because all I've done is put this down in the new denominator because it's a minus half, and then just write it as a third, and this is what we get as the final answer. Now let's look at the product rule. So the product rule, this is the general rule, which is if you have two functions, so if this is f of x and this is g of x, just how we did in by parts, we assigned u to be one of the functions and v to be one of the functions. All you do is write u as it is, multiplied by the derivative of the v, so the derivative of g of x, plus v multiplied by the derivative of u. So if you have x squared plus ln x, we assign one of these to be u and one of these to be v. So if I let x squared to be v and ln x to be u. So we want the derivative of v times u plus v times the derivative of u. And then all I've done is simplified this, written this as 2x because of the derivative, and the derivative of ln x is 1 over x. And then we have this, and then I have just cancelled out the x's and factorized. Next we have the quotient rule. So now for the quotient rule, what it's used for is basically when you have a function over a function. So all you do is g of x times, so if you have the denominator as g of x and f of x as the numerator, you do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So the way I remember this is low d high minus high d low divided by low low. So this basically means the lower function, low d high derivative of the high function minus high d low derivative of low function divided by low low, which is g of x times g of x. So if we have this is a very simple example. Derivative of high times low minus derivative of low times high, and then low low. And then I have just differentiated very simply, and we get this, and then we simplify it to this. All I've done is expanded it and subtracted the like terms. Alright. Now let's look at the last differentiation technique we need to know, which is implicit differentiation. So how implicit differentiation works is that every time you have a function of y, we multiply it by dy dx. So for instance, if you have x times y plus y sine x, So first we have to use the product rule for this because it's two functions multiplied together. If it was just x squared, then we could just differentiate it to be 2x, but since it's x times y, we need to use the product rule. So going back to the product rule, it's the derivative of one of these times the other function plus the derivative of the other function times the first function. So the derivative of x is 1 times y, so y plus x times derivative of y, which we have to replace. So derivative of y would be 1, but then we have to also multiply it by dy dx because of implicit differentiation. So it's 1 times dy over dx plus, again, derivative of y is 1 times dy dx times the other function just stays the same, plus y, keeping the first function the same, times the derivative of the second function, which is cos x. So we're using product rule for this and for this. So this is the product rule for this. This is the product rule for this. Also adding in the fact that it's implicit differentiation, so anytime you differentiate y, you multiply it by dy dx. So now all I've done is factorize the dy dx, and I get dy over dx brackets x plus sine x. And yeah, this will be your final answer. If you were to write, if they were asking you for dy dx, then you would rearrange to make dy dx on one side, and then you would just divide by this bracket just to make dy dx equal to whatever else you have left. Now let's look at another example. If you have dx over dt, so for normal maths this probably won't come up for you, but for further maths this is something that you need to look at. If you have dx over dt equals x plus 4y, and you want to find the second derivative of dx of x basically, then to differentiate this, all you do is make this into the second derivative and make x, write it as the first derivative of x, so dx over dt plus 4 times dy over dt, which is, again, if you differentiate y, you get 1, and then you have to multiply it by dy over dt because of implicit differentiation, as I showed here. So I hope that is, again, clear for you guys. Next, we're going to look at some further maths material. So these are some common integrals that you should know how to solve because they come up very, very often in complex integrals. And if you know and if you practice them from beforehand, it will make your integration much, much easier. So let's look at integrating powers of trig. Now, so before I go into how you integrate more complex integrals of trig, I want to make sure you all know what identities you will need to know for your exams. So this is so the normal trig identities are for maths as well, so make sure you write these down and make sure you have them in your notes and in your memory because these are very, very important. So let's just look at some identities for normal trig. You will need to know the double angle identity, which is where you have 2x, so that for sine 2x you will get 2 sine x cos x, and for cos 2x you have these three options, and each of these options can be equally useful because, for example, if you want to integrate cos squared x, then you would have to use this identity of cos 2x. If you want to integrate sine squared x, then you have to use this identity. We'll go into that integration in a little bit. And then for tan 2x, you would have this. And then this is a very simple one, Pythagorean's identity. And then we have these two very important ones as well, with sec squared and cosec squared. So make sure you memorize these as well. And then this is for further maths, for the hyperbolic identities. So these are the double angle ones, which you need to know. Again, very similar to the normal trig identities, but just the signs sometimes differ. So this and this is basically the same, 2 sin x cos x. but this is a plus instead of a minus, and then the cos squared is basically the same, and then the sine squared is again a difference of signs. And then again you need to know the two Pythagorean ones of sec squared and cosec squared, and these two are just basically these two rearranged, if you can see. I've just written in this form because this is what we tend to use for the integration. We tend to use this rearranged form rather than this one. So let me tell you what I mean in this example. So again, this can be used for maths or further maths. I've most commonly seen sine squared be integrated in further maths, not really maths, but if you sometimes in maths they give you a little bit more complex questions, so it might be helpful for you to know this as well in maths. So for sine squared x, what we use is the double angle identity, and we use this rearranged form here. Once we have that, we can substitute that for the sine squared x, and then we can just integrate normally. So the half will obviously become x over 2, and the minus cos 2x over 2 becomes sine 2x over 4, because you divide by the derivative of the 2x, and the minus cos x becomes sine x. So we have that there, and that's just a very simple answer here. And then again, I've shown the same thing for cos squared x. So we use the double angle identity for cos 2x. So it was, as you can see here, the identity we used was this one. So all we've done is bring the 1 plus 1 on the left hand side divided by 2, and we get this. And then again we integrate like normal, very simple integration. And then I've shown an example for sine squared x. So this is just the direct answer, but I've said here again, you have to use the double angle identity as written here. Sub that in for sine squared x, and then we just integrate like normal. So I didn't really show the whole working here because it's repetitive and it's the same as these two. And then again for the same for the cos squared x. Many times you get really long integrations for further math, so I would recommend to just memorize this rather than going through the whole process of substituting and showing that you're using double angle. But if it is a show that question, then you should show all the steps. But if it's just complex integration and it's just a small part of the lengthy integration that you have, then I would recommend just memorize this, because it will come up very, very often that they won't ask you to show all the steps. So yeah, that is for squares of trig. Now let's look at cubes of trig. So if you have sine cubed x, then the first step you should do is separate it into sine x and sine squared x. And now for sine squared x, you can use the Pythagorean identity of sine squared x plus cos squared x equals 1. So all I've done is rearrange for sine squared x and then sub that in. And then we use substitution, integration by substitution. So we use the substitution of u equals cos x, and then we find the derivative of that, rearrange it for dx. Then now we can sub in dx here, and that cancels out the sine x, and then we just integrate in terms of u, with respect to u, I mean. And then this is just a simple integration, so we get this answer, and then you can sub in your u to get this. So I hope that is clear. It's not very, very complicated, but these are the steps for it. If you had cos cubed, so if you had integrating cos cubed dx, then what you would do is separate it into this, as we have done for sine x, and for the substitution we let u equals sine x instead of cos x. So that's one thing you should remember. If you are integrating a odd power of a trig, then the substitution to use is the opposite of that trig, so it should be cos, because we are ultimately going to differentiate that to get what is here, and then that can be used to cancel out what is in the integral. So that is sort of the approach we take. So step 1 is substitute any squares that you have. Step 2 is use substitution. And then that's the same thing from here. Actually, I should make this into 3 steps. Step 1 is to separate them into odd and even powers. So the even power should probably be square, so you can use the square identity to separate it into squares. And then step 2 is use the identity, and then step 3 is use the substitution. And the same for cos cubed. Now let's look at to the power 4. This is very less likely to come up, but I just want to show you just in case you come across this question. We want to make this into a form where we can use an identity that is helpful for us. So we make this into sine squared x all squared. Now we can use an identity. Again, this is the double angle identity that we used here. Which is again similar to this one that I've showed you here. This one right here, just rearranged. And we have subbed that in for sine squared x. And now all I've done is expanded this, and I have, if you square 1 over 2, you get 1 over 4, so I'm just taking out the 1 over 4 because you can take out constants from an integral. As I've said before. So we have this integral, and now we have cos squared x here, cos squared 2x actually. So what we can do is use the cos squared x identity again, the double angle identity for it, and we get this. Again, this is actually cos 4x plus 1 divided by 2. I hope you don't get confused by this 4x, because all that is here is we have 2x here, but we have a single x here. So if you want to use for 4x, this just becomes 2 cos squared 2x minus 1. So that is all that there is, all the difference there is to it. And we have this, and now we can just integrate like normal, simple integration of trig, and this should be our final answer. Now I want to look at some trig substitution that you can use. This is only explicitly for further maths, so if you are only taking maths, then you can skip through this section. So for trig substitution, this is the most complicated integration you will probably get, because it doesn't get more harder than this. So this is one of the main rules that you should know for further calculus. So if you have an integral in the form of a over root b minus c squared x, or just root b minus c squared x. So this is very important. This is the key that you are looking at, because this is what differs for all of these. It's only what's in the surd. So for that, you use a substitution of x equals root b over root c sine x. Or if you are using hyperbolic substitution, then for that you can use root b over root c tangent x. And this b and c is the same as what's in the surd, so we're using the same constants here. So that is the rule for this. Now I will show you an example for all of them, but I just want to go through the rules first so you're familiar with them. If you have b plus c squared x, this is the form that you should look at. Then the substitution you use is x equals root b over root c tan x. Or a hyperbolic equivalent is root b over root c sine x. And then if you have c squared x minus b, then the substitution you would use is root b over root c sec x, and the hyperbolic equivalent would be x equals root b over root c cos x. Now, by what I mean by hyperbolic equivalent, it isn't necessarily that if you can choose which substitution to use. Some integrals will only work with one of the substitutions, so you really need to check which one would work. Thing that comes to you with practice, you will see similar integrals again and again, and then you can really get better and better at deciding which one to use. But if you are starting off, then just try one of them. If it doesn't work, then you try the other one. That is basically the general rules that you need to know. Some other rules that you need to know that go along with this is if there is a constant on top of the fraction, then you can use your data booklet directly and use the substitution if asked. So these substitutions, these rules of substitution that we looked through, you can do it if asked in a show that question. But usually if you do have these, then you can look at your data booklet directly. Now if I get the AQA data booklet, and you'll probably have similar booklets for similar exam boards. So if you look at this integration section, you are given these integrals. So if you have, so the ones that we want to look at in this section of trig integrals is this. So what I mean by directly use the data booklet, if you have integral in this form, then just use this rule directly. But if it is a show that question, then you might have to show the substitutions behind it. So these are the substitutions that you would need to remember to use. All you do is look at the form of the surds and then you choose appropriately. So for instance, if you have b plus cx squared and it's a show that question, then you would use this substitution. But if it's not a show that question, and if it's just a small part in your lengthy calculation, then you can directly look at your data booklet and choose appropriately whether it be this or this, and so on. As you can see, something I forgot to mention is it doesn't necessarily have to be the surd. I guess I didn't explicitly mention this, but it should only be what you are looking at to see what substitution to use is these terms here. They don't necessarily have to be under surd. All you need to look for is this term, these terms inside. So for instance, if you're looking at a over root b plus cx, then the substitution you would look at is this. And if you look at the data booklet, they are using tan as the final answer as well. So it has it's linking with the substitution that we're using. And this is again the form that they've used. As you can see, this is an a squared. And here we're using root b. So you can sort of connect that these kind of make sense on why they have given you these ready-made integrals in the data booklet and why these substitutions work. So they are connected in some form. So this might be very confusing to you if you're just introduced to this, but stick with me. We'll look at some examples and it'll be a lot clearer. All I want you to do right now is keep these rules in mind, and let's finish all the general rules so you know everything that you should memorize. So if you have a constant on top, then you can use either this data booklet directly, and you might be saying, oh, there's only a 1 here, so I can only use it if I have a 1. Well, that's not true, because if you have 1 over, so if I have, for example, 3 over root a squared plus x squared, I can write this as 3 times 1 over root a squared plus x squared. And if I'm integrating, then I can just take out the constant. So it could be 3 integral of a squared plus x squared. And then you just use this rule. So very simple. You are not just looking at 1, you are looking at any constant that can be on top. So going back to the rule, if there's a constant on top, then use the data booklet directly or use the substitutions if it is a show that question. Rule 2 is if you have a power of x on top, use substitution. Basically what I'm trying to say here is that these substitutions work even if you have an x to the power of 3 or to the power of 2 on top instead of this a. But the data booklet ones will not work because they only work for if you have constants. We'll look at some examples to clarify that. if you have an x to the power of something plus k, this something, by the way, is an integer, so a can be any real number and it has to be an integer. So x to the power of n plus k on top, then you would separate this using partial fractions, and you either have ln or arctan in your final answer when you integrate it. I will look at a very specific example for this to tell you what this means. Now, if you have root 1 over x squared plus 1, starting off with a very simple one, and you want to use the substitution, so in the rules as you saw before, for something plus x squared, you would either use sine or tan. So we have used sine, x equals sine theta here for the substitution, and as you know, for substitution we differentiate it and then we rearrange it for dx, and now we can substitute dx into this, and we can use the substitution of x for x here. Now this identity should be familiar to you because cos squared theta plus sine squared theta equals 1. So all we have done is rearrange for cos theta, and we would get for cos squared theta, and we would get for cos squared theta, and we will get 1 plus sine squared, and if we have cos, and then this just becomes cos theta because there's a root, and then we can cancel that out with the substitution. All we're left with is to integrate 1, which gives us theta, and then we can just rearrange this to give us theta equals inverse of sine x, and therefore this is our final answer. So I hope that is clear, and similar for this, instead of using the substitution, if you just want to use the data booklet, if you have 1 over root x squared plus 4, data booklet gives you this. So this is the substitution that you use. And this 4 is basically a squared. So since the general rule is x over a, then if 4 is equal to a squared, then a is obviously 2. So this becomes sine inverse of x over 2. And we don't forget the plus c. And again, using the data booklet here, we have a squared minus x squared form. So we're using this right here, which means we have tanh inverse x over a, and don't forget this 1 over a tan inverse x over a. So our a in this case would be 5, because a squared is 25. So we have 1 over 5 tanh inverse x over 5. Now I want to look at a more complex example and a shortcut that is very helpful that you can use. So this is the shortcut. If you have any integrals in the form of these, then the shortcut that you can use is 1 over root a, so whatever's in front of the x, times c, the constant on top, times the inverse of the trig, the appropriate trig that you use from your data booklet. So for example, if you have x squared minus a squared, then the trig inverse will be cos inverse. So that is all that I mean by when I say trig inverse. It's just the appropriate trig that's in the data booklet. And then inside that trig inverse would be root a, and the x form. By x form, I mean whatever form the x is given in. So sometimes they give you root a brackets x minus 1 all squared plus b. So the x form you use is x minus 1. This is the form that the x is given in. So it would just be root a x minus 1. But you know, this can be any form they give you, divided by root b. Now let's look at an example of how you use this. If you have 1 over x squared plus 27, then all you do is, sorry, ignore this. This is not correct working. And all you do is 1 over root a, so what is in front of the x, and then the trig inverse, which I've used from the data booklet, which is right here, if you can see that, and the x form, which is just x, and then root a, so root a is 3 divided by root 27, which gives you 1 over 3. So that is all that is there. So that's again a very simple rule that you can use when you want to directly use the data booklet and not do the substitution. If you have a very lengthy trig and this is only a small part, if it's only about 1 or 2 marks, then they would directly want you to use the data booklet. So this is the general rule that you can use to make your life 10 times more easier. Now I want to look at another example of the x form with the arctan or the arc hyperbolic tan, because in the data booklet there is a 1 over a, or in our case, I hope you don't get confused, the a here is different from the a that I've used in my general rule. So this a and b is what we're referring to, so don't get confused by a and b here. The only thing I would focus on to look at is the trig that you need to use, the trig form. But this is the general rule that you use, so be careful on what a's and b's you are writing down in your notes. So anyways, there is a 1 over a here, but in our case it would be 1 over b for inverse of tan, and there is a 1 over b here for inverse of hyperbolic tan. So we can modify this rule, 1 over root a times 1 over root b, because over here they used a square, so or in our case b squared. So to make this into b, obviously you have to root it. So in our case we have just used b, not b squared, so I would write this as 1 over b for our general rule. If it's too confusing to see what things you have to look at, I would just recommend memorize this rule, and for the trig inverse, just see what trig form you want to use depending on what form the integral is. So let's look at an example of using this. If you have 1 over a quadratic, they expect you to complete the square, and you should know completing the square from AS. So if you complete the square of this quadratic, you get 16 minus x plus 3 all squared. And our 16 is our b, so 1 over root b would be 1 over 4, so that's what we've done here. And we have nothing in front of the x, so our 1 over a is just 1 over root a, just 1 over root 1, so that's just 1, times the inverse of hyperbolic tan, because this is the form that we're looking at, and then multiplied by the x form, which is x plus 3 here, and root a, which is just 1 here, so root 1 would just be 1, divided by root b, which is root 16, so we have 4 here. So that is how you use these rules. These two are very, very helpful, important rules that you should memorize. If you know these, then just glancing at the data booklet, you will solve these complex surds very, very easily. Another rule I want you to look at is inverse chain rule, and how these are implemented in these complex trigs. So again, we have a quadratic here. So first step is to complete the square. And this is what we get when we complete the square. You can check this on your own as well. And if we look at the data booklet, we have an x form squared minus a constant squared. So looking at the data booklet, we have this is what we use. So cosh inverse x over a. So cosh inverse x form over a, which is root 16. Or you can just look back at the general rule that I told you. And since this x form is has a derivative that's not 1, you would have to multiply by 1 over the differentiated x form. So differentiating 2x minus 3 would give you 2. So we have to divide this by the derivative of the x form. This is what's called the reverse chain rule, and we use this in integration. So this is something that you have to remember in addition to the general rule that I've told you before. So if you want to account for that as well, all I would say is multiply this by 1 over x form differentiated. And I would add this to this rule as well. So remember the reverse chain rule that you need to use for integration. Don't disregard that in these examples as well.
And now I want to look at an example of the third rule that I gave you of when we have x to the power of a constant plus a constant in the numerator. So this is a really good exam question that shows that. So the first step you want to do is separate the x and the 2 or any constant that you have into separate fractions, because the x is going to be integrated to an ln and the 2 and the constant would be integrated to an arctan. So you want them to be separated so you can sort of integrate them separately. So as you can see here, we have used the derivative of a function over a function integral rule to integrate the x over x squared plus 9 into a half ln x squared plus 9. So the reason why there is a half there is because if you find the derivative of x squared plus 9, you get 2x. But in the numerator, there is no 2x, it is just x. So you need to multiply it by a half for that rule to work. And then if we look at our second integral, all I've done is taken out the 2 as a constant, so we can see the 1 over x squared plus 9 more clearly. And we just use our data booklet with using the rule of 1 over 3, which is the root of 9, arctan x over 3. And in the next few steps, all I've done is simplified it a bit to give you your final answer.
Now let's look at some differentiation with more complex trig. And this complex, I do not mean I mean just more complex examples of trig differentiation. So if you have yx arctan 3x, and I hope you know that arctan is just the inverse of tan. If you are confused about that, just clarifying that. So here we have one function here multiplied by another function. So we would have to use the product rule. And for that, you just assign one of the functions to be u and the other function to be v, and we just do one of the functions differentiated times the other function plus the other function differentiated times the first function. So this is multiplied by 1. So first let's look at the easier part. So differentiating x would just give you 1, so 1 multiplied by the other function. Now we have to differentiate arctan 3x. So this is arctan 3x differentiated. How do we know this? Well, we have to use the chain rule for this as well, because we have a function in a function. So we have 3x function in a function of arctan. So we have the derivative of the 3x, which is 3, times the derivative of arctan 3x. Now, in our data booklet, go to the differentiation section. We have arctan. So we use 1 over 1 plus x squared if we differentiate arctan. Since we have arctan here, but we have 3x here, all we've done is 1 over 1 plus 3x squared, because we have to keep the x form the same. And this is what we get, and all I've done is simplified that to here. So I hope you can see how we've integrated, how we've used the chain rule and the product rule here to differentiate more of a complex function. Now let's look at another example here using the chain rule, just to make sure this is a bit more clear. So we have arc cosh x over 2. So this is the hyperbolic function. So looking at the data booklet again, for arc cosh, this is what the derivative is, 1 over x squared minus 1. Now our x squared is x over 2, so we will just replace that with the x. We will replace x with the x over 2, and we have the derivative of arc cosh x over 2 multiplied by the derivative of the function in the function. So the function in the function is x over 2. So derivative of x over 2 is 1 over 2. All I've done here is just taking out the constant of 1 over 2, but this is just the derivative of x over 2. So if you are confused, I've just written it in a different form. And the derivative of x over 2 is just 1 over 2. So 1 over 2 times root square of x over 2 minus 1. And we get this. So I hope you can see how we have used all of these rules together to answer more complex integration and differentiation problems. I hope this video was helpful for you, and this is basically an all-rounder to all the things that you need to know for calculus and further maths and maths, more focused on the further maths, but we have also looked at some of the general techniques that we need to know for maths as well. So I hope this video was helpful for you. If it was, please leave a like. If you do have any clarifications of anything that I've said in the video, please again leave a comment, or you can email me as well, which is in the description. But yeah, I wish you all the best for all of the studying that you are doing, or any test exam that you have to prepare for. And yeah, bye bye.